Today we're going to be learning about probability distributions. Before we dig into probability distributions, just a few things for us to recall. First of all, that a variable is a characteristic or attribute that can assume different values. A random variable, the values are determined by chance. A discrete variable, you have a finite number of possible values, or something with an infinite number of values that we can actually count. And a continuous variable can assume values in the interval between any two given values. So the continuous variables, we had a lot of different measurements, like weights and heights and things like that. A discrete probability distribution consists of values a random variable can assume and the corresponding probabilities of the values. The probabilities can be determined theoretically, which for us, a little recall, was our classical probability, where our probabilities are determined simply from a sample space, or by observation, which was empirical probability, where we actually had to do the experiment and determine probabilities based on the data from the results of that particular probability experiment. The distributions can be shown using tables, using graphs, or formulas. We're going to focus mainly on the tables and the graphs piece. There's two requirements for a discrete probability distribution. First of all, the sum of the probabilities of all the events in the sample space must equal 1. So just a little recall for us with some of the symbols that we have here. We have our capital sigma, which tells us we need the sum. The capital P with the X in parentheses, that's the probability that our event happens. So if I add together all the different probabilities for the events in my sample space, they should total 1. The second requirement, the probability of each event in the sample space must be between or equal to 0 and 1. Remember, our probabilities cannot be negative and they cannot be greater than 1. So that's just what this little inequality shows here. All of our probabilities have to be greater than or equal to 0, but less than or equal to 1. So let's take a look at how we would actually go about constructing a probability distribution. And we're going to start pretty simple. We're going to look at if we toss two coins, and we're going to let X represent the number of heads. Let's first of all recall, I believe we've constructed the sample space before. If I toss two coins, my possible outcomes for my sample space, I could get heads on both coins. I could get tails on both coins. I could get a head on coin 1 and a tail on coin 2, or a tail on coin 1 and a head on coin 2. So the event we're looking at the number of heads. That's going to be our X. And then we have the probability of X. And if you want to rewrite as the probability of number of heads, that's okay as well. So the total possible number of heads, we might have 0 heads, we might have 1, we might have 2. And you know what numbers to put in based on your sample space. I'm not going to need to go beyond 2 because the greatest number of heads I have is 2. Smallest I have is 0, the greatest I have is 2. Now the probability that I flip two coins and I don't get any heads, 0 heads, that happens one time out of the 4 possible. That's when I flip the double tails. Getting 1 head on a coin That happens our last 2 of our sample space. So 2 out of 4. And then flipping 2 heads, that just happens once when we get the double head. So 1 out of 4 times. Should we simplify this fraction? The answer is yes. You should simplify. Our 2 requirements we talked about before said the sum of the probabilities of all events in the sample space must equal 1. So let's make sure that that holds true for us. Just a quick double check. A fourth plus a half plus a fourth, and that definitely equals 1. The second requirement we had is that all the different probabilities in our sample space had to be greater than or equal to 0, but less than or equal to 1. So no negatives and nothing larger than 1. And I look at our possibilities, and they all meet those 2 criteria. So let's go ahead, let's step it up just a little bit, something with a little larger sample space. Construct a probability distribution for rolling 2 dice, and the specific event we're going to look at is the sum of those 2 dice. So not only we're just going to look at the sample space, but more specifically, the sum of the 2 dice is the event that we're looking at specifically. So the sum of 2 dice is going to be our x, and then the individual probabilities are the p of x. Now again, we're talking about sums, so we have to think about the possible different outcomes for the sums of 2 dice. The smallest sum I could have is if I roll a 1 and a 1, the smallest sum I could have is 2. The biggest sum I could have is if I rolled the double 6, so that would be 12. So I need to go 2 all the way up to 12. Now to find the individual probabilities, if you don't have, we're not going to be able to have the sample space right here in front of us on the screen. So if you need the sample space in front of you to wonder where I'm getting these probabilities from, it's on page 187 in your textbook. So if you want to open to page 187, you can just pause me right here, open to page 187 so you can see where the probabilities are coming from. If you look on page 187, you see the whole sample space, and we can see there's 36 possible outcomes. The only way for me to get a sum of 2 is when I roll the 1 and the 1, the double 1. To get a sum of 3, if you look at your sample space, that's only going to happen if I roll a 2 and a 1 or a 1 and a 2. And then continue on. If you want to pause here and find the probabilities before I write them here, please do so. Otherwise, I'm going to continue on. Sum of 4, be a 1 and a 3 and a 1, or the 2 and the 2. So again, we're dealing with the sums. Sum of 5, 4 and 1, 1 and 4, 2 and 3, 3 and 2. For the sum of 6, that happens 5 different ways. Again, if you want to pause and figure these out, you absolutely can. 7 can happen 6 ways. 8 can happen 5 ways. 9 is 4 ways. 10 is 3. 11 is 2. And 12 is just 1, and that's when we roll the double 6. Now, should I go back through like we did up above? Should I have those simplified? Yeah, I really should. So this really should be 1/18. This really should be 1/12. One ninth. Or you can just write them below if you don't want to go back through and erase. I know it's a lot easier for me on this screen to go back and erase. than it is for you. And you actually might want to leave those there so remember where those probabilities came from, and that's fine. So all nice and simplified. Again, take some time. You always want to double check. If you add all of your probabilities together, will it equal 1? So will the sum of all your probabilities, so we're talking about adding up this row of values, do they equal 1? And that's something you definitely want to take the time to go through and check every time you create one. I know with this case there's 12 different outcomes, there's fractions, it takes a little bit to check, but that just helps you make sure that you didn't miss something or get the wrong probability somewhere. If you don't add up to 1, there's a mistake somewhere. So that's a nice double check for you. So this would be representing graphically for our distributions. Now let's talk about how we would construct a graph for that. I'm just sticking with the rolling of 2 dice. Go ahead and draw our axes in. Your possibilities, your x values, sum of 2 dice, those were our x values. Those go on our x-axis. So we would have 2, 3, 4, 11, and 12. And then your possible probabilities, those go on your y-axis. And we want to make sure that we do have a scale going up by an equal amount. So I'm going to go up by, my probabilities are all dealing with 36, so I'm going to go up by 36 each time. So 1/36. You can put 2/36 if you want, that's 1/18. 3/36 is the 12th. 4/36 is the 9th. And then we have 5/36. 6/36 is a 6th. So again, if you number them just with the 36, that's okay. And then look at your table for the corresponding probabilities. And all we do to make the graph is just draw a vertical line from our specific outcome to its matching probability. So for sum of 2 that have a probability of 1/36, so I just draw a vertical line up to 1/36. 3 had 2/36. 4 was at a 12th. 5 was at a 9th. 6 was at 5 out of 36. 7 was at 1/6. 8 was 5/36. 9 was 1/9. 10 was a 12th. We had another 18th. And we had a 36. So again, if you're asked to create a graph for a probability distribution, your possible events, your possible outcomes go on your x-axis. Their corresponding probabilities would go on the y-axis. Make sure your scale, though, goes up by an equal amount. Your probabilities might not always. This one happens to be pretty perfect that we keep going up by a 36 each time. You might have to make a scale that doesn't necessarily match right with all those probabilities. Your scale has to go up by equal amounts. So the first two we looked at dealt more with classical, aka theoretical probabilities. You have a sample space. Based on your sample space, you could find your corresponding probabilities. Now with our third example, we have a car rental agency, and it keeps track of the number of cars it rents per day for 60 days. So now we're dealing more with the empirical probability. We have actual collected data. The number of cars rented per day is represented by X. Compute the probability for each outcome. And we want to construct a probability distribution and a graph. If you want to try this on your own before I go through it, take a pause here and go ahead and try. If you want to just follow along with me, that's entirely up to you. If it were me, I would pause here and try this one myself. I always like to construct the table first. So number of cars per day is my X. And then we have my probability of each one happening. Number of cars running per day could have been 0, 1, 2, or 3 according to our data, according to our table. Now the corresponding probabilities. My total number of days is 60. So the probability of renting 0 cars, that's 10 different days out of the 60 possible. Yes, should we simplify that to 1/6? Yes, we should. Renting 1 car a day is 15 out of the 60 possible days, simplifies to 1/4. For 2 cars, that's 20 days out of the 60, or 1/3. For 3 cars was 15 out of 60, for another 1/4. Double check yourself. If you add those probabilities together, do they total 1? Is the sum 1? You have to make sure you double check that. To make the graph, drawing our axes. Number of cars per day is our X. Those are our X values. And then our probabilities are our Y values. Now we need a scale that goes up by an equal amount. With our theoretical ones, it's pretty easy to do. Now for these, our numbers are a little bit different. I don't want to have to go by 60ths. That's going to give me a lot of little increments to draw. So I'm going to look at my simplified probabilities. I have a 6, a 4, a 3, and a 4. All of those denominators can go into 12. So 12ths would be a really good scale to use. 1/12, 2/12 is just a 1/6, 3/12 is a 1/4, 4/12 is a 1/3, and we really don't need to go any higher than that, but we could put a 5/12 if you'd like. Number of cars rented per day was 0, 1, 2, or 3. 0 cars goes up to a 1/6. 1 car goes up to a 1/4. 2 cars goes up to a 1/3. And 3 cars is back at a 1/4. So this one doesn't make quite that perfect symmetric shape that our rolling of 2 dice did. Or if we would have done it for flipping 2 coins, it would have worked out to be nice and symmetric as well. Oftentimes your more classical or theoretical probability distributions, oftentimes the graph turns out to be a lot more symmetric than if you just have empirical data. Now I want to make sure that I really hit home the idea of what is okay for a probability distribution and what some of the flaws might be. I'm going to make our table there. What I want you to do, take a pause here and see if you would say that each of these is an okay probability distribution or if there's something wrong. Does it not meet one of the 2 requirements? So take a pause here, see what you think of each of these 3. If we look at letter A, a couple of characteristics that we have to make sure are met. Does the sum of our probabilities, does it equal 1? Well, if I take 3/10 plus 4/10 plus 4/10 plus 1/10, I actually end up with 1.2, not 1. So letter A is not a probability distribution. It's not a probability distribution. If we look at letter B, if I add together a half and a 16th, 2/7, and 17 112ths, the sum of our probabilities equals 1, so that first requirement's met. The second requirement says all of our probabilities have to be greater than or equal to 0, so no negatives, or less than or equal to 1, so nothing bigger than 1. All of our probabilities check out, so this is an okay probability distribution. Last but not least, if I add together the sum of our probabilities, I end up with 1.5, not 1, so it strikes out on the first one. But the other thing we also want to note is we have a negative probability Probability cannot be negative. That's just one of our basic rules of probability also, not just because it's a probability distribution. And a probability cannot be greater than 1. Please make sure, read section, this should be 5.1. Make sure you read section 5.1 if you haven't yet, which you probably haven't. And then these are the homework questions, assignment questions, if you will, that I'd like you to try. So the rest of the time's yours. Please make sure again that you actually read through this section. I didn't hit on every single little thing possible, so make sure you read through the section. And then the rest of the time is yours to read and also work on the assignment piece.